So let's continue on from my last video about characteristic subgroups. This problem here in particular is demonstrating the transitivity of characteristic subgroups. So it's asking to show that if H is a characteristic subgroup of N and N is a characteristic subgroup of G, then H is a characteristic subgroup of G. So before we begin, let's remind ourselves what it means for a subgroup to be characteristic. So I have a definition here. So a subgroup H of G is called a characteristic subgroup of G if for any automorphism, in this case I use phi, so for any automorphism phi of G, when you apply phi to H, you get back H. So H remains invariant under any automorphism of G. We know that being characteristic is a stronger statement than being normal. So we know that H characteristic in G is a stronger statement. I'm going to just write char. H characteristic in G is stronger than H being normal because if you're characteristic, then you are normal. But being normal does not imply characteristic. We also know that transitivity does not hold for normal subgroups. So H being normal in N and N being normal in G does not imply that H is normal in G. You can quickly find a counterexample for this if you look within the dihedrals or the symmetric groups. I'm sure you'll find an example there. And then last time we proved that H being characteristic in N and N being normal in G implies that H is a normal subgroup of G. So this is what we showed last time. And now what we want to show is what happens if N is also characteristic in G. So now we want to show if H is characteristic in N and N is characteristic in G, does this imply that H is characteristic in G? So do characteristic subgroups have this transitivity property? So now that we got all that good and insightful information, let's go ahead and begin our proof. So we're going to suppose that H is characteristic in N and that N is a normal subgroup of G. We're going to just pick some automorphism of G. So we're going to use phi. Let phi be an automorphism of G. And what we want to show is that phi of H is equal to H. Let's recall that N is characteristic in G as well. So N being characteristic in G, this tells us that phi of N is equal to N. That's just a definition of being characteristic. But a little bit further, the restriction of phi to N is an automorphism of N. So the restriction of phi to N is an automorphism of N. In other words, phi, and I'm going to denote the restriction of phi to N with a little n underneath, is an automorphism of N. Similarly, if we restrict the restriction of phi to N and we restrict it further to H, no, we don't need to restrict any further because H is characteristic in N, and we know that the restriction of phi to N is an automorphism of N. Since H is characteristic of N, then the restriction of phi to N, we apply this to H, it's going to give us back H. That is, H is equal to phi, the restriction of phi to n applied to H, but this is actually just the same as applying phi to H. Thus, H is characteristic in G. And that completes the proof.